Today we're going to talk about differentiation of vector functions. What does it mean to take the derivative of a vector function? Well, let's start with the vector function r of t, whose components are the regular scalar functions f of t, g of t, and h of t. By definition, r prime of t will just be the limit as delta t approaches 0 of r of t plus delta t minus r of t over delta t. This is exactly analogous to the definition of the derivative for a regular old scalar function, except now we have a difference of vector functions here, and by dividing by delta t is the same as just multiplying by the scalar 1 over delta t. We already talked about what it means to take a limit, so let me write how we can do that. We can write r prime of t is this limit, which is just a limit as delta t approaches 0 of what is r of t plus delta t? Well, that's the vector f of t plus delta t, g of t plus delta t, h of t plus delta t, minus r of t, which is just f of t, g of t, h of t, all over delta t. And we can rewrite that very easily. In the first component, we have f of t plus delta t minus f of t from the first component on the right over delta t. In the second component, we have g of t plus delta t minus g of t over delta t. And in the third component, we have h of t plus delta t minus h of t over delta t. Then when we take the limit, we take the limit component by component. And you all know the limit as delta t approaches 0 of the first component is exactly f prime of t. The limit as delta t approaches 0 of the second component is exactly g prime of t. And the limit as delta t approaches 0 of the third component is exactly h prime of t. So again, this tells you that you can take derivatives of vector functions component-wise, one component at a time. How do we interpret these? Well, one way to interpret the derivative is when we think of r of t, this vector function, as specifying the position of an object at time t. In other words, this space curve that you get from r of t corresponds to the path the object moves, starting from, say, t equals a and ending at t equals b. This vector function specifies that motion, and the derivative of the vector function, r prime of t, is what we're going to call the velocity vector, v of t. And of course, we already just saw that r prime of t is just f prime of t, g prime of t, h prime of t. Along with that, I want to note that the velocity vector will always be a vector that's pointing in the direction of motion, precisely because of how r prime of t is defined. Moving from r, you're looking at this limit of the vector r of t plus delta t minus r of t times the scalar 1 over delta t. So you're asking what is that vector movement over a small time period, delta t, and then you're scaling it up by dividing by delta t. This velocity vector will always be in the direction of motion, and the length of the velocity vector is what we'll call the speed, v of t. Here's where it's going to be very important that you use vector notation properly. The vector function v of t, which when handwritten will be a v with a vector hat on it, that's the velocity vector. V of t without a vector hat on it will denote the speed at time t. And it's just the length of that velocity vector. And of course, that's just the length of this vector. That's going to be the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. That's our speed function. The derivative of that velocity vector, which is the second derivative of the position vector function, will be called the acceleration. And that's a vector function, the second derivative of the position function. And in coordinates, that's just given by f double prime of t, g double prime of t, and h double prime of t. That will point in the direction in which the velocity vector is changing. So that acceleration vector tells you not just the magnitude of how the speed is changing, but also it tells you the direction in which the velocity vector is changing. Here's a quick example. Let's say we have r of t as cosine 2t, sine 2t, and 5t. And here, I believe I've computed this, or shown the picture when t runs from about 0 to 6. You see when t is 0, we start at the vector 1, 0, 0. That's this vector here that points in this direction. There's the x-axis. This x actually refers to that axis down there. And this is the y-axis here. So here's the x-axis, and here's the vector 1, 0, 0. That's a vector from the origin to that point. And remember, we'll think of the path of the object as the set of points there at the tip of these vectors. So this is exactly r of 0. We can compute the velocity vector, which is just r prime, and that's the vector minus 2 sine 2t, 2 cosine 2t, and just 5. That tells you the direction the object is moving. As an example, when t equals 0, the velocity vector at time 0, you plug in 0, you get exactly 0, 2, 5, and that would be a vector that's kind of up in this direction. That would, at the initial time 0, the position of the object is here, at the, corresponding to 1, 0, 0, that position, and the velocity vector, which is shown here, 0, 2, 5, shows you the direction the object is moving. And at any other time, we can plot here, say, what is v? Let's start with r of pi. When you plug in pi, cosine of 2 pi is just 1. Sine of 2 pi is 0. But now we're all the way up here at 5 pi. Actually, this isn't t going from 0 to 6. I see here we're only having t go from about 0 to a little bit bigger than 2. So pi is off the picture. So let me change this example. Sorry for that mistake. Let's look at that. There's nothing wrong with that except it would just be way up high off the picture. Let's look at r of pi over 2. When t is pi over 2, we're at position cosine of pi, which is negative 1, sine of pi, which is 0, and the z-coordinate is 5 pi over 2. 5 pi is 15.5, almost 16, so this is a little bit less than 8. So you can see where we are here. We're at x is negative 1, y is 0, but we're way up here. So we're kind of at a point here just below 8, right there on the curve. How does the velocity vector point here at pi over 2? We can see that that's the vector. Negative 2 sine of 2 pi, that's going to be 0. 2 cosine of pi, which is negative 2. And 5. So here you see it's a vector like this, showing the direction in which we're going. Let's go one step further and compute the acceleration, which is the derivative of the velocity, which is the second derivative of the position function. We'll just differentiate this velocity function and we'll get minus 4 cosine of 2t minus 4 sine of 2t and 0. One thing you'll see is that other than the scaling factor of -4, that looks just like r here with a 0 in the z-coordinate. Because that scaling factor is -4, is negative, the acceleration will be kind of in the opposite direction of the position vector, ignoring the z-coordinate. So at the beginning, the acceleration is pointing towards the z-axis. In fact, always this acceleration vector will point directly towards the z-axis, and it'll be pretty long here because of that 4 there. So wherever the object is, the acceleration vector just points you right back towards the z-axis. So the velocity is always changing to keep it rotating around the z-axis. And you can see this space curve is a helix, just like the earlier example we had in a previous video lecture.